Now in this lecture we'll find out the radius of the small circle. In the drawing we have this small circle and a semicircle, and this small circle is inscribed by the semicircle. We know that line segment CD equals to 3 units, line segment DB equals to 4 units, angle CDB, this angle is a right angle, it is equal to 90 degrees, and we want to find out the radius of this small circle. Okay, so first of all, we'll do a construction. We'll complete the semicircle, we'll complete this semicircle to a circle. Okay. So we completed the semicircle to a circle. In the next step, we will extend the straight line CD by a straight line until it touches the circle. And we will define the touching point of the extended line segment CD with this circle as point E. So here we actually extended the straight line CD by a straight line. So if you extend a straight line by a straight line, the result must be a straight line. So the result is line segment CE, that it is a straight line. So we know that CE is a straight line, and we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles must be equal to 180 degrees. So which angles we have at this side of C at point D? We have here 90 degrees and angle EDB. In total, the sum of those two angles must be equal to 180 degrees. So I write it down here. $90 degrees plus the size of angle CDE, EDB, the size of angle EDB. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So here we will subtract 90 degrees from this equation, and we'll get that angle EDB, the missing angle, equals to 180 degrees minus 90 degrees, it is 90 degrees. So angle ADB is a right angle, it is equal to 90 degrees. So you can write here that this angle in EDB is equal to 90 degrees. Okay. So actually, when we completed the semicircle to a circle, we created a second semicircle that is a mirror image of the original semicircle. I repeat again, the new semicircle that we created is a mirror image of the original semicircle. Okay, and Here angle CDB, this angle equals to 90 degrees, and this angle EDB is also equals to 90 degrees. Okay, and actually we extended the straight line CD by a straight line. We created line segment DE. Actually we created the mirror image of line segment CD. The mirror image of line segment CD is DE. And because of the fact that DE is the mirror image of CD, it must be equal to CD in its length, but it will be in the opposite direction. Exactly like if you look at yourself in the mirror, you see yourself exactly in the same dimensions as you are, but in the opposite direction. Okay, so actually here we get that CD is equals to DE. CD is equals to DE by symmetry. That is to say, DE is the mirror image of CD, and therefore the length of DE must be equal to the length of CD, but it is in the opposite side. Okay? Exactly, when you see yourself in the mirror, you see yourself exactly in the same dimension as you are, but in the opposite direction. Therefore, CD is the same length of DE, but in opposite direction. That is to say, CD equals to DE by symmetry. Okay? But CD equals to 3 units according to what is given in the question. So we can write here that CD equals to 3 units. And from this equation, 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. DE is also equals to 3 units. Okay, so we can write here that DE equals to 3 units. In the next step, I will present to you a new rule that is actually rule number 1. According to rule number 1, if two circles have an internal length between them, then the straight line that connects between their centers passes through the launch point. From the launch point of the two circles. And the launch point it is the point of tendency or touching point between those two circles. Point of tendency between those two circles, or the touching point between the two circles. So I'll read rule number 1 again. According to rule number 1, if two circles have an internal lunge between them, then the straight line that connects between their centers passes through the lunge point of the two circles. And the lunge point is the point of contact or point of tendency between those two circles. So here I will explain what is the meaning of rule number 1. We have this circle, and in this circle we have two chords that intersect with each other inside the circle. We have here, this is chord AB, this is chord AB, and chord AB intersects with chord CD inside the circle. This is chord CD, and you can see from the drawing that chord AB intersects with chord CD. At this point, we define the point of tendency, the intersection point between those two chords as point O. Again, chord AB intersects with the red chord CD at point O. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then according to rule number 1, we will get that AO times OB equals to CO times OD. I'll repeat again. AO times OB equals to CO times OD. Okay, so if you have two chords that intersect with each other inside the circle, here chord AB intersects with chord CD at point O, then according to rule number 1, AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. And actually, we can implement rule number 1 in our drawing, because in our drawing we have chord AB. This is chord AB that intersects with chord CE at point D. I will repeat again. Chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. So I write it down. In our original drawing, we have chord AB. This is chord AB. Intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Okay? I'll repeat again. Chord AB intersects with chord, again, chord AB intersects with chord CE as point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we get that AD times DB equals to CD times DE. I'll repeat again. According to rule number 1, AD times DB equals to CD times DE. Okay? Here AD is the missing line segment, so we will leave it as it is. AD times dB. According to what is given us in the question, dB equals to 4 units. So we'll substitute dB by 4. And it is equal to CD, that is 3 units, times DE, that is also 3 units. So actually, in conclusion, we found out that according to rule number 1, AD times 4 equals to 3 times 3. 3 times 3 is 9. So AD, 4 AD equals to 9. 4 AD equals to 9. Here we divide this equation by 4 and we get that AD equals to 9 over 4. We found out that AD equals to 9 over 4. So we can write here that AD equals to 9 over 4 units. And we also know that AB is the diameter of the circle itself and also the diameter of the semicircles. Okay, so AB is the diameter of the circle and the semicircle. I write it down. AB is the diameter of the circle and also the diameter of the semicircles. And we know that the diameter of any circle or semicircle is twice as long as the radius. So actually, if AB is the diameter, we have to divide it by 2 in order to get the radius of the circle and the semicircle also. We will define the radius of the big circle and also the radius of the semicircles as capital R. Therefore, the diameter AB over 2 will be equal to the radius of the circle and also the radius of the semicircles. Okay. So here AB, from the drawing you can see that AB equals to AD plus DB. AB equals to AD plus DB. And if we divide it by 2, we get the radius. So here AD equals to 9 over 4. And dB equals to 4 units according to what is given us in the question. All divided by 2. Here we'll multiply 4 by 4 and then we'll divide it by 4 in order to have a common factor with 9 over 4. So here we'll get that 9 plus 4 times 4 is 16 over 4 over 2. 16 plus 9 is 25. We will move to the denominator, so here it will be 4 times 2. So in conclusion, we found out that the radius of the circle and also the radius of the semicircles, it is equal to 25 over 4 times 2 is 8. Okay, so the radius of the circle and the semicircles, it is equal to 25 over 8 units. Okay. In the next step, we will define the center of the small circle as point Q, and we will define the radius of the small circle as small r, and we will define the center of the big circle and the semicircle as P. This is the center of the big circle and also the semicircles. So the center of the big circle and the semicircle is at this point, point P, and the center of the small circle is at this point, point Q, and its radius is small r, is equal to small r according to our definition. Okay, so here we will draw from point Q radius to the point of tangency of tangent dB with this small circle. Here we will define the point of tangency of line segment dB with this small circle as point M. Point M is the point of tendency, and then from point Q we will draw radius to the point of tendency, that is to say to point M. First of all, QM is the radius of the small circle. Why QM is the radius of the small circle? Because of the fact that it starts from the center of the small circle and then at point M, that is a point on the small circle itself. And this is exactly the definition of a radius. That is to say, QM is the radius of the small circle. That is to say, it is equal to small r. So here we have the radius QM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent dB with this small circle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. Here the tangent dB will be perpendicular to the radius of QM. Again, tangent dB will be perpendicular to the radius QM, So if DB is perpendicular to QM, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, from the center of the small circle, that is to say from point Q, we'll draw the radius to the point of tendency of tangent CD with this small circle. We will define the point of tendency of tangent CD with this small circle as point O, and here line segment QO is the radius of the small circle. Why? Because it starts from point Q, that is the center of the small circle, and then at point O, that is a point on the small circle itself. This is exactly the definition of a radius. So here we have the radius QO. The radius QO that is equal to R, it is drawn to the point of tendency, that is to say it is drawn to point O, that is the point of tendency of tangent CD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius OQ. Again, CD is perpendicular to OQ. If CD is perpendicular to OQ, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Now we will focus on quadrilateral QOMD. In quadrilateral OQDM, we have 1, 2, 3 right angles. Again, 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle OQM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. I repeat again, in quadrilateral OQDM, the sum of all of its 4 angles must be equal to 360 degrees. So the sum of the 3 angles is, it has 3 right angles, and the sum of 3 right angles is 270 degrees, plus the size of the fourth angle, that is actually angle OQM. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we will subtract 270 degrees from this equation, and we will get that the missing angle OQM is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. Okay, so here, this is a right angle. Angle OQM is a right angle. So therefore, in quadrilateral OQDM, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle. So we relate to quadrilateral OQDM as a rectangle. Okay, quadrilateral OQDM is a rectangle. Why? Because it has 4 right angles. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle OQ DM, in rectangle OQDM, we'll get that OQ equals to DM. I'll repeat again. In rectangle OQDM, OQ equals to DM. Okay, here OQ equals to DM according to the rule that the opposite sides of a rectangle are equal to each other. Here, but we have already found out that OQ equals to R. It is the radius of the small circle, it is equal to small r. So we can write here that OQ equals to small r, that is the radius of the small circle. And from this equation, r equals to OQ equals to dm, we will derive that dm is also equals to small r. dm is also equals to small r. So we can write here that dm equals to small r. It is the radius, small r, that is the radius of the small circle. Okay? And what is the length of dp? The length of the short line segment dp from the drawing, it is very easy to see that the length of the short line segment dp equals to db minus pb. I'll repeat again. The length of the short line segment dp equals to db minus pb. Okay, here dp equals to db minus pb. Here db equals to 4 units according to what is given us the question, so we'll substitute db by 4. And what is the definition of line segment PB? P is the center of the big circle. B is the point of the big circle itself. And this is exactly the definition of a radius. I'll repeat again. P is the center of the big circle. B is the point of the big circle itself. Therefore, PB is the radius of the big circle. That is to say, it is equal to capital R. So in conclusion, we found out that dp equals to 4 minus r, 4 minus capital R, but capital R equals to 25 over 8. We have already found out that capital R equals to 25 over 8 units. So we'll substitute capital R by 25 over 8. So in conclusion, we found out that dp equals to 4 minus capital R, that is 25 over 8. So dp equals to 4 minus 25 over 8. So here we will multiply 4 by 8 and then we will divide it by 8 in order to have a common factor with 25 over 8, and we will get that dp equals to 4 times 8 is 32, so it is 32 minus 25 over 8. So dp equals to 32 minus 25 is 7, so in conclusion dp equals to 7/8. So dp equals to 7/8. So we can write here that dp equals to 7/8. And what is the length of line segment PM? What is the length of line segment PM? This line segment PM. From the drawing, it is very easy to see that the length of line segment PM is equal to dm minus dp. I'll repeat again. PM equals to dm minus dp. Here, PM equals to dm minus dp. That is to say, PM equals to dm equals to small r, according to what we have already found out. So we will substitute dm by small r minus dp. dp equals to 7/8. So in conclusion, we found out that PM equals to R minus 7/8. Small r minus 7/8. So we can write here that PM equals to small r minus 7/8. Okay. Here we will define the launch point or the point of tangency or the point of contact of the big circle with the small circle. Here we'll define this point that is the launch point as point S. So right here, that point S is the launch point of the big circle with the small circle. The launch point, we can define it also as the point of tendency of the big circle with the small circle, or we can also define it as point of contact. Okay? The point of contact of the big circle with the small circle. Okay? And in the next step I will present to you a new rule, that is rule number 2. According to rule number 2, if two circles have an internal notch between them, like in this drawing, the big circle and the small circle have an internal notch between them at point S. Okay, here, this point S, that is to say they are touching each other internally, while they are touching each other internally, because the small circle is inside the big circle. Okay, so point S is the launch point. So if two circles have an internal launch between them I repeat again that in our specific drawing, the internal length between the big circle and the small circle is at this point, point S. And it is internal length, it is defined as internal length because of the fact that the small circle is located inside the big circle. Okay, so those two circles have an internal length between them at point S. Okay, so if two circles have an internal length between them, then the straight line that connects their centers passes for the launch point of the two circles. Okay, so I'll read rule number 2 again. According to rule number 2, if two circles have an internal length between them, then the straight line that connects their centers passes through the launch point. And as I already said, the launch point is the point of tendency or point of contact. In our specific drawing, the launch point, those two circles have an internal length between them, and the launch point is located here at point S. And according to rule number 2, we get that those two circles have an internal length between them, and according to our definition, point P is the center of the big circle, point Q is the center of the small circle. And according to rule number 2, the straight line that connects between their circles, between their centers, is PQ. Again, PQ, line segment PQ is the straight line. This line segment PQ is the straight line that connects their centers together. So I will draw it in the red color. Again, PQ is the line segment that connects between their centers, and according to rule number 2, this straight line PQ passes through the launch point. That is to say, the straight line PQ passes through point S, that is the launch point between those two circles. So according to rule number 2, points P, Q, and S are located on the same straight line. Okay? So in our original drawing, according to rule number 2, points P, Q, and S are located on the same straight line, or that is to say, PQS is a straight line. Okay, on PQS, line segment PQS is a straight line according to rule number 2. PQS is a straight line according to rule number 2. Okay, so what is the definition of line segment QS? Q is the center of the small circle. S is a point on the small circle itself. And this is exactly the definition of a radius. So QS is the radius of the small circle, that is to say it is equal to small r. And what is the definition of line, the straight line segment, the straight line PS? The definition of PS, P is the center of the big circle, S is the point of the big circle itself. That is to say, PS is the radius of the big circle that is equal to capital R. And capital R, we have already found out that capital R equals to 25 over 8 units. Okay, PS equals to R, the capital R, that is 25 over 8 units, and QS equals to small r, it is the radius of the small circle. Therefore, what is the length of PQ? From the drawing, it is very easy to see that the length of line segment PQ it is equal to PQ. This line segment PQ equals to PS minus QS. Again, the length of this line segment PQ equals to SP minus SQ. We can say that PQ equals to PS minus QS. It doesn't matter. So here, I repeat again, we found out that PQ equals to PS minus QS. But according to what we have just right now found out, that PS equals to capital R. So we substitute PS by capital R, and QS equals to small r. So in conclusion, we found out that PQ, the length of line segment PQ, equals to capital R minus small r. And we have also found out that capital R equals to 25 over 8 units. So we substitute capital R by 25 over 8, and we get that PQ, in conclusion, PQ equals to capital R, that is 25 over 8 units, minus small r. So we actually found out that the length of this line segment PQ equals to 25 over 8 minus r. If PQ equals to 25 over 8 minus small r. So we can write here that PQ equals to 25 over 8 minus small r. Okay? now we'll implement the Pythagoras theorem on the green right triangle, triangle QPM. The only missing variable in this triangle is small r. That is the thing that we are looking for in this lecture. We want to find out the value of small r, that is actually the radius of the small circle according to our definition. So we will implement the Pythagoras theorem on this right green triangle, and in this way we will find out the value of small r, that is actually the radius of this small circle. That is the thing that we are looking for in this lecture, to find out the radius of the small circle. Okay? So we copy the right triangle PQPM in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle QPM. So this is the right triangle QPM that I copied from the original drawing. We've already found out that PQ equals to 25 over 8 minus small r. We have already found out that PM equals to small r minus 7/8. And we have already found out that QM equals to small r, is the radius of the small circle. Okay, so we have the values of all the three sides of the right triangle QPM. Okay, this is the right triangle QPM. So here by PT is the abbreviation for Pythagoras theorem. We'll get that according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay? The hypotenuse is PQ, so the square of the hypotenuse is PQ squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QM squared plus PM squared. Okay, so according to the Pythagoras theorem, in this right triangle, triangle QPM, PQ squared equals to QM squared plus PM squared. Okay. PQ equals to 25 over 8 minus small r. We'll square this expression and we'll get PQ squared. QM equals to r, so QM squared is r squared plus PM squared. PM equals to small r minus 7/8. We'll square this expression in order to get PM squared. So, we found out that 25 over 8 minus r squared, according to equation number 1, it is equal to r squared plus r minus 7/8 squared. We will open the brackets on both sides of this equation, equation number 1, And we get that according to equation number 1, 25 over 8 minus r square, it is 25 over 8 square, that is 25 square, that is 625, over 8 square, that is 64, plus r square, minus 2 times 25 over 8 times r, and it is equal to r square plus r minus 7/8 square. It is equal to r square plus 7/8 square is 49 over 64 minus 2 times r times 7/8. Okay. So here we have r square on both sides of this equation, equation number 1, so r square will get cancelled. After we cancelled r square, we left here with 625 over 64. And here we have minus 2 times 25 r over 8. So we will divide both the numerator and the denominator of this expression by 2. And we get that minus 2 over 2 is minus 1. So minus 2 will get cancelled. And we left only with minus 25r. And here in the denominator we have 8, so 8 over 2 is equal to 4 because we divided both the numerator and the denominator by 2. So this, in conclusion, this expression equals to minus 25r over 4. And it is equal to r squared plus 49 over 64 here we have minus 2r times 7 over 8. We divide both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so minus 2 will get cancelled. And we left with minus 7r. In the numerator we have left only with minus 7r. Over in the denominator we have 8, and 8 over 2 is 4. So in conclusion, this expression minus 2r times 7 over 8 equals to minus 7r over 4 after we divide it by 2. Okay? So in conclusion, we got this expression. Here we multiply this expression, this equation by 64. And we get that 64 over 64 is 1. So we left only this expression equals to 625. Here we have minus 25r over 4. We multiply it by 64. And here minus 64 over 4 is minus 16. So this expression equals to, in total, to minus 16 times 25r over 4. And it is equal to 64r squared, because r squared times 64 is 64r squared. And here we have 49 over 64, and 64 over 64 is 1, so 64 will get cancelled, and we left only with 49. So this expression equals to 49. And we have here minus 7r over 4, that is multiplied by 64. It is actually minus 64 over 4, that is minus 16 times 7r. So this expression in total equals to minus 16 times 7r. After we multiply it by 64, it is equal to minus 16 times 7r. So here we have, according to equation number 1, we found out that 625 here we have minus 16 times 25r equals to minus 400r. And it is equal to 64r squared plus 49 here we have minus 16 times 7r is minus 112r. So here we will add 400r to this equation, equation number 1. And according to equation number 1, we get here, we have here 625. 400r minus 400r is 0, so in this side of the equation we left only with 625, that is equal to 64r squared plus 49, and here we have 400r minus 112r, it is equal to 288r. So I repeat again, 400r minus 112r equals to 288r. So in conclusion, I found out that according to equation number 1, 625 equals to 64r squared plus 49 plus 288r. Okay. In the next step, we will subtract 625 from this equation, equation number 1. And we will get that according to equation number 1, (64r squared plus 288r. Here we have 49 minus 625. It is equal to minus 576, and it is equal to 0. So in conclusion, we found out that according to equation number 1, 600r squared plus 288r minus 576 equals to 0. So here we divide this equation by 32, and we get that according to equation number 1, (64 over 32 is 2, so this expression equals in total to 2r squared. Here, 288 over 32 is 9r. And minus 576 over 32 is minus 18. That is equal to 0. So here we have the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18. And remember that we are looking for in this specific quadratic equation is x equals to r. And the general formula for solving out a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. Okay, and in our specific quadratic equation, the variable that we are looking for is r, so here we substitute x by r, and r equals to minus b equals to 9, so minus b is minus 9, plus minus square root of b squared, b equals to 9, so b squared is 9 squared, that is 81, minus 4 times okay, so it is minus 4 times a is 2 times c is minus 18. All divided by 2a. A is 2, so 2 times 2 is 4. So in conclusion, we found out that r, small r equals to minus 9 plus minus, and inside the root we have 81, and here we have minus 18 times 2 is minus 36, and minus 36 times minus 4 is plus 144. So in conclusion, inside the root we have 81 plus 144, all divided by 4. So r, the radius of the small circle, equals to minus 9 plus minus 144 plus 81 is 225. So inside the root we left only with 225 over 4. So here r, the radius of the small circle, it is equals to minus 9 plus minus, the square root of 225 is 15, all divided by 4. So here we will have two solutions that are possible for r, the radius of the small circle. The first solution is r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24. And minus 24 over 4 is equal to minus 6. So according to the first solution, the radius of the small circle equals to minus 6, that is a negative number. So here the radius of the small circle, we are talking about the length of the radius of the small circle. So r is the length of the radius of the small circle, and r is a length. It must be a positive number. It must be a positive number. Therefore, it cannot be equal to minus 6, that is a negative number. So we will cancel the solution and we're left only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6 over 4. So I found out that r equals to 6 over 4. We divide both the numerator and the denominator of this expression by 2. 6 over 2 is 3 and 4 over 2 is 2. So in conclusion, I found out that r, the radius of the small circle, it is equal to either 3 over 2 units, or in terms of numbers, it is equal to 1.5 units. Okay, r, the radius of the small circle, equals to either 3 over 2 units, or in terms of numbers, it is equal to 1.5 units. In the next step, I will summarize the lecture. Okay? So actually, in the drawing we have a circle that is inside a semicircle, and we know that side CD equals to 4 units, side DB equals to 4 units, angle CDB, this angle is a right angle, it is equal to 90 degrees, and we want to find out the radius of this small circle that is inscribed by the semicircle. Okay? So actually, in the first step, we did a construction. We completed the semicircle to a circle. Again, we completed the semicircle to a circle, and then we extended line segment CD of the straight line CD by straight line until it touches the circle at this point, point E. Point E is the touching point of the extended line segment CD and the circle. And actually CD is a straight line. When we extended the straight line CD by straight line, the result must be a straight line. So CE must be also a straight line, because when you extend a straight line by straight line, the result must be a straight line. So CE, it is a straight line. And we have the rule that the sum of the angles from one side of a straight line is equal to 180 degrees. So we'll focus on this side of the straight line CE at point D. The sum of the angles must be equal to 180 degrees. Again, at this side of the straight line CE at point D, the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have here at point D? We have here 90 degrees, and we have this angle that is actually angle EDB. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So 90 degrees plus the size of angle EDB, in total they must be equal to 180 degrees according to the rule that I mentioned. We subtract 90 degrees from this equation, and we get that the missing angle EDB equals to 180 degrees minus 90 degrees, it is 90 degrees. So this angle EDB equals to 90 degrees. Okay? And here, so we know that angle CDB equals to 90 degrees, and angle EDB also equals to 90 degrees. And actually, when we completed the semicircle to a circle, we created a second semicircle. This semicircle that we created is a mirror image of the original semicircle. I repeat again, the new semicircle that we created by completing the semicircle to a circle is the mirror image of the original semicircle. Okay? And then when we extended line segment CD by a straight line, we created the mirror image of CD. ED that we created is a mirror image of CD. And we know that when you look at the mirror, you see yourself exactly with the real dimensions of yourself, but in the opposite direction. Exactly in this case, it is also the same case that here the mirror image DE must be equal to CD in its length, but it is in the opposite side. Okay, again, the mirror image DE of CD must be equal to, so DE, that is the mirror image of CD, must be equal to it in its length. Okay, here, because of the fact that DE is the mirror image of CD, they must be equal in their lengths, and the only difference between them is in their direction. DE is the opposite, in the opposite side of the direction CD. They have a common point, that is point D. Point D is the common point, and here DE is in the opposite side of CD, but the lengths of those two line segments are equal to each other because DE is the mirror image of CD. Therefore, DE equals to CD by symmetry. Because of the fact that DE is the mirror image is CD, they are equal in their lengths. That is to say, CD equals to DE by symmetry. So, and because of the fact that CD equals to 3 units, we can write here that CD equals to 3 units. And from this equation, 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Here, DE equals to 3 units. Okay? In the next step, I presented to you rule number 1. According to rule number 1, if two circles have an internal length between them, then the straight line that connects between is actually rule number 2. This is actually rule number 2. And here we are relating to rule number 1. And according to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true, that AO over AO times OB, AO times OB equals to CO times OD. Okay? I repeat again on rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true, that AO times OB equals to CO times OD. Again, we have here chord AB that intersects with chord CD. It's point O. Point O is the intersection point of chord AB with chord CD, the right chord. So in this situation, if this is the data that has been given to us, then according to rule number 1, we get that AO times OB equals to CO times OD. I repeat again, AO times OB equals to CO times OD. Okay, So we can implement rule number 1 in our drawing. Why? Because in our drawing we have chord AB that intersects with chord CE at point D. Again, chord AB intersects with chord CD at point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to, I'll repeat again here, that chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we get that AD times DB equals to CD times DE. Again, AD times DE equals to CD times DE. AD times DB equals to CD times DE according to rule number 1. AD is the missing line segment. DB equals to 4 units according to what is given us in the question. So we substitute DB by 4. CD equals to 3 units according to what is given us in the question. So we substitute CD by 3, and we have already found out that by symmetry DE also equals to 3 units. DE equals to 3 units. So in conclusion we found out that AD times 4 equals to 3 times 3. 3 times 3 is 9. So 4 times AD equals to 9. We divided this equation by 4 and found out that AD, the missing line segment, equals to 9 over 4. Here, AD equals to 9 over 4. Okay? So we know that AB is the diameter of the circle and also the diameter of the semicircles. And we know that, okay, so here AB is the diameter of the circle and also the diameter of the semicircles. The circle and the semicircles have the same diameter, that is AB. Okay, and we know that the diameter of any circle or semicircle is twice as long as the radius. Okay, the diameter of any circle or semicircle is twice as long as the radius. So if we define the radius of the semicircle and the radius of the big circle also as capital R, we'll get that AB over 2 will be equal to capital R. Okay? AB over 2 equals to capital R, because the diameter is twice as long as the radius. So if we divide the diameter by 2, we get the radius that is capital R according to our definition. So what is the length of AB? AB equals to AD plus DB. AB equals to AD plus DB. Okay? All divided by 2, it is equals to capital R. AD equals to 9 over 4, and DB equals to 4, all divided by 2. Here we multiplied 4 by 4, and then we divided by 4. In order to have a common factor, we have 9 over 4. So 9 plus 4 times 4 is 16, over 4 over 2. 16 plus 9 is 25, over 4. We moved the 2 to the denominator and found out that the radius of the big circle and the radius of the semicircle is equals to 25 over 4 times 2. 4 times 2 is 8, so in conclusion found out that the radius of the big circle, that is also the radius of the semicircles, capital R, it is equal to 25 over 8 units. Okay? Then we defined the center of the big circle, this is also the center of the semicircle, is point P. This is the center of the big circle, point P. And we defined the center of the small circle, this point is point Q. Okay? And from point Q, we drew a straight line to the point of tendency of tangent CD with this small circle that is point O. Again, from point Q, we draw the radius to point O, that is the point of tendency of tangent CD with this small circle. And whenever you draw a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent CD will be perpendicular to the radius OQ. So if CD is perpendicular to OQ, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Very simple. Likewise, from point Q, we do the radius to point M, that is actually the radius QM, that is equal to small r, it is drawn to the point of tendency. That is to say, the radius QM, that is the radius of the small circle, it is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent DB perpendicular to the radius MQ. If DB is perpendicular to MQ, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. So actually, in quadrilateral OQDM, in quadrilateral OQDM, we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the form angle, that is actual angle OQM. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, here we subtracted 270 degrees from this equation, and we found out that the missing angle OQM equals to 360 degrees or 270 degrees, it is 90 degrees. So here this angle equals to 90 degrees. Okay, so actually in quadrilateral OQDM we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we will relate to quadrilateral OQDM as a rectangle. So in rectangle OQDM, the opposite sides are equal to each other. We know that the opposite sides of a rectangle are equal to each other. Therefore, in rectangle OQDM, its opposite sides must be equal to each other. That is to say, OQ must be equal to DM. OQ must be equal to DM according to the rule that the opposite sides of a rectangle are equal to each other. Okay? But we have already found out that OQ equals to R, it is the radius of the small circle. It's correct here that OQ equals to small r, and from this equation R equals to OQ equals to DM, we will derive that DM is also equals to R. Here, DM, this line segment DM equals to small r, that is the radius of the small circle. Then we found out the length of the small line segment DP. From the drawing, it is very easy to see that the length of line segment DP equals to DB minus PB. Again, DB minus PB equals to DP. I'll repeat again. DP equals to DB minus PB. Okay? So dP equals to dB equals to 4 units according to what is given as the question. Minus PB. P is the center of the big circle. B is the point of the big circle itself, and this is exactly the definition of a radius. That is to say, B equals to the radius of the big circle, that is capital R. Okay, so in conclusion, we found out that dP that is equals to dB minus PB, it is equal to 4 minus R, minus capital R. But we have already found out that capital R equals to 25 over 8. So we can substitute capital R in this equation by 25 over 8. So we did it, and we got that dp equals to 4 minus capital R, that is 25 over 8. Here we multiplied this equation by, we multiplied 4 by 4, and then we divided, we multiplied 4 by 8, and then we divided by 8 in order to have a common factor with minus 25 over 8. And we found out that here dp equals to 4 times 8 is 32, and 32 minus 25 is 7. So in conclusion, we found out that dp equals to 7/8. Here, the length of this small line segment, dp equals to 7/8. And what is the value of the length of line segment PM? From the drawing it is very easy to see that PM equals to dm minus dp again. dm minus dp equals to PM. Okay, again, here, PM equals to dm minus dp. dm equals to small r, the radius of the small circle. dp, we just right now found out that dp equals to 7/8. So in conclusion, we found out that PM equals to small r minus 7/8. Here, PM equals to small r minus 7/8. Okay, in the next step, I presented to you rule number 2. According to rule number 2, if two circles have an internal notch between them, then the straight line that connects their centers passes through the launch point of the two circles. So, what is the meaning of rule number 2? The meaning of rule number 2 is that if we have in this our specific drawing, the small circle is located inside the big circle, and those two circles have an internal notch between them at point S. Point S is the launch point, or the point of tendency, or the touching point of the small circle with the big circle. Okay? So, in our specific drawing, we have an internal notch between the big circle and the small circle at point S. Therefore, according to rule number 2, the straight line that connects the two centers together, that is to say PQ, the straight line PQ, passes through the launch point that is actually through point S. That is to say PQS is one straight line, or points P, Q, and S are both points P, Q, and S. All those 3 points are located on the same straight line, or PQS is one straight line. Okay, because of the fact that there is in our drawing an internal notch between the small circle and the big circle at point S, then according to rule number 2, the straight line PQ that connects the centers of the small circle with the big circle passes through point S. That is the launch point of the two circles. That is to say, PQS is one straight line, or points PQ and S are located on the same straight line. Okay, here the conclusion from rule number 2 is that points P, Q, and S are located on the same straight line. Okay, or PQS is a straight line. PQS is a straight line according to rule number 1. Okay. And what is the definition of QS? Q is the center of the small circle. S is point on the small circle itself. This is exactly the definition of a radius. That is to say, QS equals to small r is the radius of the small circle. QS is the radius of the small circle, that is to say it is equal to small r. And here PS, what is the definition of line segment PS? The definition of line segment PS, P is the center of the big circle, S is a point on the big circle itself, and this is exactly the definition of a radius. That is to say PS is the radius of the big circle that is equal to capital R, and capital R equals to 25 over 8. So PS is the radius of the big circle, and QS is the radius of the small circle. Therefore, PQ, this line segment PQ will be equal to PS minus QS. Again, PS minus QS equals to PQ. Okay, here again, PQ equals to PS minus QS. We have already found out that PS is the radius of the big circle that is equal to capital R. So we substitute PS by capital R, and QS equals to the radius of the small circle that is small r. So we substitute QS by small r. So in conclusion, we found out that PQ equals to capital R minus small r. But capital R equals to 25 over 8 according to what we have already found out. So we can substitute capital R by 25 over 8. And in conclusion, we found out that PQ equals to 25 over 8 minus small r. Here, PQ equals to 25 over 8 minus small r. In the next step, I copied the right great triangle PQM in a new page and we implemented the Pythagoras theorem on this right great triangle QPM. In this right triangle PQM, the only missing variable is small r, that is the radius of the small circle. So by implementing the Pythagoras theorem on this right great triangle, we'll find out the value of the length of small r, that is the line segment that we are looking for to find in this question. We want to find in this question the radius of the small circle that is actually the small r. Okay, so I copied the right triangle QPM in this new page. We know that QP equals to 25 over 8 minus r, PM equals to r minus 7/8, and QM equals to small r. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PQ square equals to MQ square plus PM square. So here PQ equals to 25 over 8 minus r, so PQ square is 25 over 8 minus r square, and it is equal to QM. QM equals to r, so QM square is r square, plus PM square. PM equals to r minus 7/8, so PM square will be equal to r minus 7/8 square. We open the brackets on both sides of this equation, equation number 1. Here we have 25 over 8 minus r square. It is equal to 25 over 8 square. That is 25 squared, that is 625 over 8 squared, that is 64. Plus r square minus 2 times 25 over 8 times r. In the other side of the equation we have r square plus r minus 7/8 square. It is equal to r square plus 7 over 7/8 squared, that is 7 squared, that is 49 over 8 squared, that is 64. Minus 2 times r times 7/8. Okay. So here we have r square on both sides of the equation, so r square will get cancelled. And here we divided both the numerator and the denominator of this expression. So here 2 will get cancelled, and 2 over 8 over 2 is 4. So in conclusion, this expression equals to minus 25r over 4. And this expression, we have minus 2r times 7 over 8. We divided both the numerator and the denominator by 2. Minus 2 over 2 is 1, so 2 will get cancelled. and here 8 over 2 is 4. So in conclusion, this expression equals to minus 7r over 4. Okay, and we got this equation number 1. That 625 over 64 minus 25r over 4 equals to r squared plus 49 over 64 minus 7r over 4. We multiply this equation number 1, by 64. Here we have 64 over 64 is 1, so 64 will get cancelled, and we have to leave with 625. Here we multiply this expression by 64, and here we have minus 64 over 4, that is minus 16. So in conclusion, this expression, after we multiply it by 64, it is equal to minus 16 times 25r. Minus 16 times 25r. And here we have 64 times r squared equals to 64r squared. Here we have 49 over 64 times 64 equals to 49. And here we have minus 7 over 4 times 64. It is actually minus 64 over 4, that is minus 16. So in conclusion, this expression, after we multiply it by 64, equals to minus 16 times 7r. Okay, so here we found out that, according to equation number 1, 625. Here we have minus 16 times 25 equals to minus 4, and again, minus 16 times 25r equals to minus 400r. In the other side of equation number 1, we have 64r squared plus 49, and here we have minus 16 times 7r equals to minus 112r. Here we subtracted 400r from this equation number 1, and here we get 625, and here we have 400r minus 400r is 0, so here we left only with 625. Here we have 64r squared plus 49, and we have here 400r minus 112r, it is equal to 288r. So in conclusion, we found out that according to equation number 1, 625 equals to 64r squared plus 49 plus 288r. We subtracted 625 from this equation number 1. So here 625 minus 625 is 0. And here we have also 664r squared plus 288r. And here 49 minus 625 equals to minus 576. Okay, so in conclusion, we found out that according to equation number 1, 64r squared plus 288r minus 576 equals to 0. Here we divided this equation number 1 by 32, and we got that 64 over 32 equals to 2, so this expression equals to, in total, to 2r squared. 288r over 32 equals to 9r, and here minus 576 over 32 equals to minus 18, and all equals to 0, because 0 over 32 equals to 0. So we have the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18. And the variable that we are looking for in this specific quadratic equation is r, so x equals to r. And the general formula for solving out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So in our specific quadratic equation, the variable that we are looking for is r, so x equals to r, so we substitute the x by r. and it is equal to minus b. b equals to 9, so minus b is minus 9 plus minus b squared. b is 9, so b squared is 9 squared, that is 81. Minus 4 times a is 2, and c is minus 18, divided by 2a. a is 2, so 2 times 2 is 4. Okay, so here we have inside the root minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So inside the root we left only with 81 plus 144, and then we have minus 9 plus minus square root of 81 plus 144 over 4. And this 81 plus 144 is 225. So in conclusion, we found out that r equals to minus 9 plus minus square root of 225 over 4. So here r equals to minus 9 plus minus the square root of 225 is 15, all divided by 4. So here we have two solutions that are possible for r. The first solution for r is that r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r equals to minus 6, that is a negative number, but here r is the length of the radius of the small circle. So r is the length, and as a length it must be a positive number. It can never be equal to minus 6, that is a negative number. So we cancel this solution, and we have to only with the second solution, that r, the radius of the small circle, equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4. We divided both the numerator of 6 over 4 by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r, the radius of the small circle that we are looking for, it is equal to 3 halves, 3 over 2, or 3 halves, or in terms of numbers, it is equal to 1.5 units. I repeat again, the radius of this small circle, that is to say small r, equals to either 3 halves, or in terms of numbers, it is equal to 1.5 units. Okay, thank you very much.